Well, today is the day you have been waiting for. At least if you're trying to look for shortcuts and easy way of doing things. But that's not what we're about really. But today our focus is going to be on how to use our calculator to determine derivatives at different points. Now obviously this is not something that we want to lean on too often, but sometimes we have functions that just are so ridiculously complicated that we know what to do with it, and we're trying to apply our knowledge of calculus to the real world. So it's less about performing algebraic manipulation and derivatives and things like that analytically, and it's more about how do we use it. And so we'll just plug into our calculator and use it. So today we're going to learn how to use our calculator to determine derivatives at different points. Before we do that, I want to look at an example that we can actually figure out without a calculator. And the purpose of this is so that we can verify that what the calculator is giving us is correct. So our first example is, it says f of x equals 1/4 x squared. F of x equals 1/4 x squared. And it's asking us to find the derivative. Well, for number one, find the derivative function. And then for number 2 and 3, find the derivative at particular points. So obviously it's going to be beneficial for us to figure out the derivative function first, because then we can plug in the -1 and the 2 into the function instead of having to redo the whole thing for each one. So remember, the definition of derivative is f prime of x is equal to the limit as h approaches 0 of f of x plus h minus f of x all over h. And again, remember that's x plus h minus x, but that will always cancel out, so we can just simplify it to that. Now, we're going to go ahead and plug those two values in, if you would. X plus h in and x in, if you would. So limit as h approaches 0 of 1/4 of x plus h squared. That's the y2, and then minus y1 is just the original function, so 1/4 x squared, all over h. And then we're going to go ahead and simplify this. The limit as h approaches 0. And then multiplying all this out, we end up with 1/4 x squared plus 1/2 xh plus 1/4 h squared, and then minus the 1/4 x squared here, all over h. We can see that the 1/4 x squared and the negative 1/4 x squared are going to cancel out. And we can also see that the remainder of that has a common factor of h. So I'm going to go ahead and take that out right now. So this is gone, take out a factor of h. We're left with 1/2 x plus 1/4 h all over h. We can see that the h is reduced, and then we can plug in 0 for h. And so we can say that f prime of x is equal to, plugging in 0 there, we'd end up with 1/2 x plus 1/4 times 0, or just simply put 1/2 x. So here's number one. We have the derivative function, 1/2 x. Okay. Number two is asking for the derivative at a specific point. So we're looking for the derivative at -1. So f prime of -1, we can just take that -1 and plug it into our derivative function. That's going to be 1/2 of -1, which is -1/2. Okay, so we've got that. And then, of course, if we had some sort of application like find the tangent line at x equals -1, then we would have to figure out what the value of at -1 is and then create the point slope form. But we're not concerned with that today. So f prime of 2, well, that's going to be 1/2 of 2, which is 1. And so there's our answer there. So again, this is number one. It's good practice in the definition of derivative and how to work with that. But number two, we want to use this as a basis to figure out how to use our calculator to determine these two values. Now, one thing I'm going to tell you about your calculator, the TI-89 is very intelligent, if you would. It's a pretty useful calculator. It's capable of figuring out derivative functions. A lot of calculators can't do that. Most of them can figure out the derivative at points, because they look at it, the calculator kind of thinks through it the same way as you would, moving that point closer and closer, the second point closer and closer to the first point until it appears to be a tangent line. So it actually goes through the work of that. But the TI-89 calculator can actually figure this out. Now, with that said, you should not ever be using your calculator to determine the derivative function. There will never be a context on any assessment, including the AP exam, where you would use that. And if you do use that, then you're depending too much on the calculator. You need to make sure that you know how to find derivative functions by yourself without the use of technology, okay? The purpose of the calculator is to calculate derivatives at certain points efficiently when we have really, really complex functions that we need to take the derivative up. So I'm just giving you that warning. Never rely on your calculator to figure out a derivative function, okay? Now with that said, make sure I got those right, looks good. Now you can ignore this whole thing. This is actually for a TI 83. No, this is the TI-89. It's just written weird. But I guess you can look at that. We're going to go over. I'm going to jump over to my computer here so I can use my simulator. All right, so I'm on my simulator now, and our goal is to figure out what the derivative is at the 2 points, -1 and 2, of the function that we were talking about over on the whiteboard. So the first thing I want to do is go to my Y list. So I'm going to hit the green F1 button, and I'm going to go ahead and type in the function that I'm looking at. I'm looking at 1/4, so 1 divided by 4, x squared, so x raised to the second power, and then we'll hit enter. And again, always make sure that what you have typed here matches the function that you want, that you didn't forget a parenthesis and then the x squared ended up in the denominator or something like that, okay? So it looks like I'm good there. And then we're going to go to the home screen, so hit home, and then this is the keystrokes that you're going to type in for derivative. There's a couple different ways of doing that. I will show you both of them. But the first one is your F3 button. You can see all these buttons up here. You can hit F3 to pull down your calculus options, calculus, and then you see all these different options. You would hit differentiate, derivative, differentiate. This is the focus of first semester really. And then integrate will be the focus of second semester. You can also see some other things in there. There's your limits and different things like that. But our focus in here is going to be the derivative. So we can either hit the number 1 and that will move us to there, which is already there, or we can scroll down to what we want. But I wanted number 1, so I'm going to hit enter. So that brings up D as in delta. So take the derivative of. And now you would type in your function. So I could type in 1/4, 1 divided by 4, x raised to the second. I could type that in here, but and that's fine if you do. But remember, I have it stored in my Y list. So I'm going to go ahead and delete this. And I had it stored in Y1. So I'm going to type in Y1 parentheses x. So by doing this, close parentheses, that brings up the function that's saved in my Y list, okay? It was particularly the Y1. The next thing you're going to type is comma x. So what this is the Y1 says refer to the Y list. The parentheses x says we're looking at that function in terms of x. Then the comma x tells us we're taking the derivative in terms of x. And later on we're going to talk about taking derivatives in terms of other variables. But in this case it's in terms of x. Then you're going to go ahead and close the parentheses, and then you're going to put evaluate, the evaluate button, when x equals -1. Okay? So the derivative of my function in respect to x evaluated when x equals -1. That's the common procedure in determining that. So then you hit enter. And you can see that we get -0.5, which is exactly what we got when we did this analytically on the board, when we proved it on the board. So that's kind of cool. I'm going to go ahead and do the other one, the f prime of 2, but I'm going to show you just one quick keystroke, and it's not necessarily less keystrokes, it's just a different place. Notice that this is the derivative, the delta. we actually find the delta right here. It's the blue button right above the 8. So if you could hit the second 8 button, there's your derivative again. Okay, second 8, and then you type in the function again, and I'm going to go ahead and type the function in this time. So 1 divided by 4x squared. So that is my function. Then we hit comma x, so take the derivative in respect to x, close our parentheses, and then evaluate when x equals, in this case, x equals 2, and then hit enter. And we end up with 1, just like what we did before. So now you know how the keystrokes of figuring out the derivative at a point with your calculator. Now, like I said before, you are capable, or your calculator is capable, of figuring out the derivative function. So I'm going to show you that, but I don't want you to depend on it. It's just a good resource if you ever need it. So you would hit the same keystrokes, basically, the derivative, so second 8, or F3, and then type in your function, 1/4 x raised to the second, and then comma x, close parentheses. And instead of saying evaluate when x equals 2, we can just hit enter, and it gives us our function. Our derivative function is 1/2 x, and that's exactly what we came up with, or x over 2, same thing. Okay. Again, you can just type in what you have in your y list, and again, that's probably the best way of doing this. So with that said, real fast keystrokes, you would push the home button. Make sure you're in that home screen. You hit F3 and then 1, or you can hit the second and the 8 button. And then you type in the function, 1 divided by 4, x raised to the second, then comma, then x, and then close the parenthesis that was already brought up, and then evaluated when x equals -1 or x equals 2 or whatever point you're looking at. All right, and then hit enter after that. Okay, what I want you to do now is our goal is to kind of be able to discover something here. We're going to use the idea of using our calculator to find derivatives because we don't know the derivative function of natural log of x. So we're going to explore it, we're going to discover it here. So what I want you to do is I want you to figure out the derivative of natural log of x for all these x values. So notice the table is g prime of x. Okay, so find the derivative at point 1, the derivative at point 3, the derivative at point 5, just like we did up here, not the derivative function, don't cheat on me now, the derivative at different points. And then you'll plug those, or you'll input those points here in the table, and then I want you to plot those points now on a scatter plot. So you may not know how to do that with your calculator. That's okay. If you want, you can use Desmos to do that, and that's all right if you want to do that. But you can plot those points, and then our goal is to figure out the function that is produced when we take the derivative of natural log of x. And you're going to find that it's actually a pretty cool relationship here. So go ahead and pause the video, spend some time figuring out these values, plotting the points, and then when you're ready, come back on here and see how you did. All right, so I'm going to clear this out. And I'm going to go up to my y list, and I'm going to type in, clear that out, I'm going to type in natural log, so it's going to be second natural log, it's right there, of x, and I'll close those parentheses. So there we have the function in our y list, and just for good measure, looking at the graph, we're going to hit the diamond and F3. So you guys should be familiar with the idea of natural log of x. It's got a vertical asymptote when x equals 0. And it hits the x-axis at 1, 0. So that's the graph. I'm going to go to the home screen and I'm going to figure out what some of these values are. So derivative of y1 parentheses x, close parentheses, comma x, close parentheses, evaluate when x equals 0.1. Hit enter, so we get 0.1 out. That's great. Now I'm going to push my right arrow button and delete the 0.1, and I'm going to put 0.3 and hit enter. Okay, and I'm going to delete that, and I'm going to put 0.5, so I don't have to retype it in every time, and I get 2 there. I'm going to plug in place of 0.5, I'm going to put 0.8, get 1.25. And then I'm going to plug in 1, and I end up with 1. That's kind of cool. We'll talk about more of that in the future. We'll plug in 2, and we get 0.5. And so you can see that as we go further and further to the right, our derivative is actually getting smaller. Okay, it's getting smaller. That's kind of neat. Let's see what happens. 6, you get 0.1667. 8, we get 0.125. Interesting. How about 10 here? We end up with 0.1. Let's go kind of extreme. Let's go to 50 and see what happens. Well, I've seen a pattern here. I see that the derivative is decreasing, meaning it's kind of flattening out in a sense. So look at that, 0.02. Let's go ahead and type in 100 and see what happens. If I plug in 100, I end up with 0.01. Okay. What about 1,000? I end up with 0.001. Interesting. What about 10,000? Interesting, 0.0001. So as I go further and further in towards x equals infinity, you can see that the derivative of natural log of x appears to be approaching 0. Okay? So what I'm going to do with that, I'm going to go ahead and write these values down in my lesson here, so we have that as a reference. And then I'm going to go to Desmos, and I'm just going to type these in as coordinates. In fact, I'll create a table here. That'll be probably the quickest way of doing it. So 0.1 is 10, 0.3 is 3.333, and I'm assuming that's going to repeat. 0.5 is 2, 0.8 is 1.25, 1 is 1, 2 is 0.5, 4 is 0.25, 6 is 0.167. I believe that's going to be 1.66666, so on. 8 is 0.125, and then 10 is 0.1, and then we can keep going with that. But if you look at these points on this graph, I'm going to go ahead and hide the table here. If you look at these points on this graph, these look like they are points that lie on a very specific function. Okay, so what function does that look like? Well, it appears that I have a horizontal asymptote of y equals 0, and it also appears that I have a vertical asymptote of x equals 0. So which function has a vertical and a horizontal asymptote both of 0? Well, let's go ahead. You might be able to see this. Let's go ahead and type in the function that you think. How about y equals 1 over x? And there you go. Those points lie perfectly on the rational function y divided by x. Now, we didn't check the negative values here, and why couldn't we do that? Well, because if I'm thinking back to my natural log function, right? My natural log function, the domain of natural log is all positive values of x. So this part of the domain, or this part of the derivative, doesn't exist for natural log of x. Okay? So that's kind of cool. And then let's go ahead and graph the natural log of x so we can compare it side by side in a sense. Y equals natural log of x. We'll put that right next to that graph. In fact, let me go ahead and change the domain of 1 over x. I'm going to change that to be for x greater than 0. That way we have only the part of the function that we care about. So the red function was my original g of x. And then the black function here, and I'll go ahead and change that to green just because the points are plotted green. Okay. So our green function is the derivative of the red function. Notice what's happening. We can see that the red function is increasing. It's always increasing. It will never go downhill. In fact, as I zoom out, you can see it's never going to go downhill. It kind of flattens out in a sense, but it never goes downhill. It's always increasing. Well, that would imply that the derivative is always positive. If the function is always increasing, that means when I draw a tangent line, the tangent line will always have a positive slope, which means the derivative will always have a positive value. And you can see here that all of these values on the green function, the derivative function, are all positive values. They're all above the x-axis. So that makes sense. And then we can see as the red graph, natural log of x, goes on, we can see that it's getting flatter and flatter and flatter. Okay? So what can we say then? That would imply that the derivative is approaching 0 because the tangent lines are becoming flatter. That means the slopes of them are getting closer and closer to 0, and so we can see that. And since the function never goes decreasing, then we will see that the derivative will never be negative. Over here, we can see that the function is really, really steep, really close to the y-axis. That would imply that its derivative is really, really big. The slope of the tangent line is really, really big because that would be a really steep tangent line. And that's why we have values that are very big close to the y-axis for the derivative. So that's kind of cool there. We see that the derivative of natural log of x is 1 over x. Now, I want that to be committed to memory. I will go through and prove that with you at a later time when we have a deeper understanding of how to take derivatives analytically. But for now, whenever you see natural log of x, you should recognize that the derivative function of natural log of x is 1 over x. And there's a domain restriction for all x values greater than 0. Okay? So I'm going to go ahead and jump back over to the whiteboard so we can continue on with our discussion. All right, so looking at the next slide here, these problems that I'm going to talk about are actually not problems on the TI-89. When I created this lesson, I didn't have an 89 necessarily, I had an 83. And a lot of the things are similar, but the 83 has some problems. So I'm not going to go into depth with this particular problem here, but I'm going to go ahead and just move on to our exit problem because this lesson is actually pretty quick here. So this exit problem says, let f of x be a piecewise function where the first piece is the cosine of x for x is less than pi over 2, and then negative, parentheses, x minus pi minus 1 over 2 squared, and then plus 1/4. That's an interesting function there. X is greater than or equal to pi over 2. And that's my piecewise. Okay. The question is f differentiable at x equals pi over 2? Is f differentiable? Now remember, there's 3 parts to differentiability. Number 1, f must be, so we're going to ask these questions. Is f continuous, okay, when x equals pi over 2? Okay, that's the first question. The next question is, what is f prime of pi over 2 from the left? And what is f prime of pi over 2 from the right? And we have to see if those are equal. And then we have to see if f prime, overall, f prime of pi over 2, is some constant value, not infinity or negative infinity. Now, if this is true, and if this is true, then we have a function that's differentiable at pi over 2. Now, we don't know, we can figure out if f is continuous without a calculator. But we don't know how to find the derivative of cosine yet. Now, in a previous lesson, I had you guys kind of experiment with the sine function, and you should remember that the derivative of sine of x is cosine of x. Some of you might want to extrapolate on that and say, well, then the derivative of cosine of x is sine of x. No, it's not. Good try. But it's closely related to it. So if you want, on your own, you can go ahead and graph cosine of x and then play around with graphing points of its derivative. So when is the derivative 0? When is it positive? When is negative? And you should see a relationship. We will get more into that in the future. But we don't know how to do this yet unless we experiment with that first. So I'm going to allow you to use a calculator for this part, and then of course this will be easily seen after we determine this. So go ahead and pause the video, see what you come up with, and then when you're done, come back and see the results. For the first part, I want to know if f is continuous at pi over 2, so I'm checking to see if I want to know if f is differentiable at pi over 2, so I'm checking to see if f is continuous there. So remember, there's 3 things to check there. We have to check the limit as x approaches pi over 2 from the left of f of x. We have to check the right-hand limit and the function's value. Well, for this guy, the limit as x approaches pi over 2 from the left, we're going to use the cosine piece. So that's going to be the cosine of pi over 2. And what's the cosine of pi over 2? Well, the cosine of pi over 2 is 0. Okay, so we have that. And then the limit as x approaches pi over 2 from the right of f of x. Let me get rid of this real fast. We'll put that down later. Okay, we're going to use the bottom portion of this piecewise. So it's going to be negative pi over 2. Oh, we got, yeah, that's right. Minus pi minus 1 over 2 squared plus 1/4. Why can't I use a calculator on this? Because you don't need it. You just don't need it. I'm going to go ahead and, these have the common denominator here, so it's going to be pi minus, I'm going to put that in parentheses, pi minus 1 all over 2, common denominator, squared plus 1/4. So you might be able to see that we're going to get a fourth here, so we get negative. And then when I square all this, let me simplify this. Pi minus pi is 0. Negative minus 1, or negative 1 times negative 1 is positive 1, so I got 1/2 squared there. And then I've got, ultimately, that's going to be 1/2 squared, 1/4. That's a negative 1/4 plus 1/4 is 0. So we can see that the left-hand limit equals the right-hand limit. That's good. And the last thing we need to figure out is f of pi over 2. I'm not going to show all that work because we're going to use this part of the function to figure out f of pi over 2, because that's the equal sign. We already did all that work there, and we ended up with 0. So as a result, we can say f is continuous when x equals pi over 2, since limit as x approaches pi over 2 from the left equals the limit as x approaches pi over 2 from the right equals f of pi over 2. So that's good. We got the limit, or we got the function is continuous. All right, the next thing we need to figure out is we need to figure out what f prime of pi over 2 is from the left, and then we'll also need to figure out what f prime of pi over 2 is from the right. We need to see if those match. And so this is where we're going to be able to use our calculator to determine this. And so just going to do it off my normal TI-89 here. Going into the y list. Boy, that's an ugly function. That really is. But we're going to have to do it anyways. Okay. So let's see. Cosine of x, first of all. So the derivative of cosine of x, comma x, close parentheses, evaluated when x equals pi over 2. And we should get -1. So we are using, I typed in the derivative of this guy at pi over 2 because I wanted the left-hand derivative. Now the right-hand derivative, I'm going to use the bottom function, and that is probably, you probably could simplify that a little bit, but I'm not going to. So negative parentheses x minus, now here's where it gets weird. You got to make sure your parentheses match, or you're going to have to add parentheses to make this turn out the way you want it to, okay? And so make sure when you hit enter on this, whoops, that what is being produced here, it matches exactly what that says. So I typed in the function, now comma x, close parentheses, evaluate when x equals pi over 2, and hit enter. Okay, I got a syntax error. What's going on here? There we go. And I end up with 1 here. Now, I didn't check. I'm going to go back in and look to see if what I have makes sense. And I don't. In my expression, I am missing the negative here. But I did end up putting the x minus pi minus 1 over 2 squared plus 1/4 correctly. So I'm just going to go back into that. And I'm going to put the negative out front of that and see if that works. I got the negative there. And yeah, so I missed that negative, so that actually becomes -1 right there, okay? So now we can see that f prime from the left and f prime from the right are the same. And because they are numeric values and not infinity, then we can say all three things are met. So we could say f is differentiable when x equals pi over 2. And so that is our answer. There we go. Okay. Now, what does that mean graphically? Well, we know that cosine, the cosine function, looks something like this, right? And pi over 2 is going to be right here. So the part of the function that's in this piecewise is just to the parts to the left. Now this function is a quadratic. This function's a quadratic, and it opens down. So we can see that we have a vertex of positive pi minus 1 over 2, comma 1/4, and it opens down. So, but what I do notice about this is that since it had the same slope at this point, we know that it's going to trend like this. And because it's opening down, it's not going to bounce back up like this, because that wouldn't make sense. Since this is going down, it's got to keep going down and getting steeper, because the parabola is going to actually be on this side of it. That's the only way it can open down. So that's kind of what this graph looks like. Notice it's smooth here, it's continuous, it's smooth, and it's not vertical. That's essentially differentiability. It's continuous, okay? It's smooth, that's why these derivatives are the same, and it's not vertical. It's steep, but it's not vertical, okay? So that wraps up this lesson in how to use your calculator to find derivatives. This is a good tool to experiment and explore all different types of functions. If you don't know derivative functions yet, if you don't know how to figure out what those derivative functions are, you can use your calculator to play around like we did, creating tables of different derivative values and seeing what those functions look like and getting an idea of what that function could be. Now that's not the be-all end-all. The goal is to know how to take the derivative. But it's a good way to experiment and discover through it. And we'll talk about how to actually analytically do all this stuff later on. But otherwise, if you have any questions for me, please leave a comment below or reach out to me and I will gladly help you out. I hope that you got something good out of this. I hope that you were excited to use your calculator. It's probably been a little while there. Now, just fair warning, our next lesson is actually how to take a derivative, or some derivatives, without doing all the big, long definition of derivative. The limit as h approaches 0 of f of x plus h minus f of x all over h. We're going to learn how to get derivatives of specifically polynomial functions without doing all that work. And so when you talk about shortcuts, that's the real shortcut. And it's not a fake shortcut like your calculator. It's legit. It's called the power rule. We'll talk about it next time. Until then, have a great night.